The body metabolizes fast, sometimes too fast. Certain drugs can be metabolized and eliminated from the body way faster than the time it takes them to make the desired effects. To solve this problem, sustained release capsules were invented. This kind of technology plays a huge role with efficiency and dose accuracy. For example, instead of a person taking 3 or 4 pills in a single day, the patient only has to take one single pill. This pill would be a sustained release capsule that would progressively release the drug into the patient's body. The main advantages here are less waste of non-absorbed drugs by the body and a better dose control. In this project, a sustained release drug capsule will be analyzed from the point of view of mass transfer and diffusivity. This spherical gel capsule contains a saturated solution of drug, in this case called solute A. It also contains a lump of solid species A, which, as long as it exists, keep the concentration of A within the core constant. The objective here is to develop an analytical integrated equation to determine the total rate of drug release, WA. The assumptions to solve this problem are: the mass transfer process is carried in a steady state. As the gel capsule is spherical, the best coordinate system is spherical coordinates. There is one-dimensional flux along the radial direction. There is no reaction in the system, which means RA becomes 0. Temperature and pressure remain constant during the analysis. Diffusivity and concentration are constant. The concentration of solute A in the mixture AB is so close to 0 that the advective term in Fick's law becomes 0. As a first step, Fick's law is applied. From the unimolecular diffusion assumption, the advective term becomes 0, getting the following equation, where the vector NA looks like this. In the model there's only radial transfer, so we get equation 1. The second step is to apply the mass transfer equation. As the process is in a steady state and there is no reaction, the equation can be reduced to this. For spherical coordinates and assuming radial transfer, the nabla operator looks like this. Simplifying the equation, we get here. Then it can be concluded from this equation that the flux remains constant respect to the radius. Therefore, the equation can be solved through the integration method. Okay, finally the solution. So the rate of drug release is given by the mass flow, which is given by the flux times the perpendicular area. From equation 1 we get here. In this case, the area changes as the radius changes. For a sphere, the area is given by the following formula: 4 times pi times r squared. Thus, we get this equation. In this equation, the dependent variable is the concentration YA, and the independent variable is the radius r. As the mass flow WA is constant, it is possible to solve the equation using the integration method and the proper limits. The boundary conditions. The maximum solubility of the drug in the gel capsule material is 0.01 grams per cubic centimeter. The maximum possible rate of drug release from the capsule will be given when the concentration in the outer radius approaches to 0. So we were standing here. By integrating on both sides and applying the boundary conditions, we get this pretty equation. After solving the integral and solving for WA, we get the final equation. Computing the initial information, we find the maximum possible rate of drug release from the capsule, which is 3.17 milligrams mole per hour. We've seen how the utilization of mass transfer and Fick's law can be used to solve or analyze all kinds of different problems, including problems in the field of medicine. As a future work, pill-shaped capsules, which are commonly used, could be analyzed using different coordinate systems. For example, dividing the structure of a pill in a cylinder with one semisphere on each end could give us an appropriate analysis for the capsules that are actually used, giving our analysis even more accuracy. Thanks for watching.